Hi, in this video I'm going to estimate the amount of charge transferred from a neutral sweater to a neutral balloon. So let's get started. Here I have a picture of my setup where after frictional charging the sweater attains positive charge and the balloon attains negative charge. I have a thread attached to the balloon which in turn is attached to a solid surface. The reason I have this is to make sure that the balloon is in a stable equilibrium setup. So now let's get into the assumptions I'm making in the video. I'm taking the mass of the balloon to be 5 grams. So I came up with this number by estimating the mass of the balloon to be around the same as the mass of this piece of paper, which is around 5 grams. I'm taking the angle to be 45 degrees just to make the calculations easier, but we can measure this angle nonetheless. And the radius of the balloon, the inflated balloon, I'm taking to be 5 centimeter. The reason I took this number was I estimated the radius of the balloon to be half the size of a soccer ball, which is the size of a soccer ball is around 22 centimeters, and estimating this inflated balloon to be half of that is pretty reasonable. And other main assumption I'm making in the video is I'm taking the balloon to be a point charge, so all the negative charge is centered around the center of the balloon. That means the distance between the charges is equal to the radius of the balloon. Also, the charge lost by the sweater is equal to the charge gained by the balloon. And finally, the thread is taut and has no friction. That means there is no friction in this setup, and this is a frictionless setup. So now let's get into the force diagram part of our calculations, where I have in the x direction force of electrostatic and T sine, the horizontal component of the tension, and in the y direction I have the force due to gravity and the vertical component of the tension. So since the balloon is in a state of equilibrium, we can say mg is equal to t cos theta, which gives us t to be equal to mg divided by cos theta. And in the x direction we can say force of electrostatic is going to be equal to t sine theta. And if we substitute this equation for force of electrostatic, we get this. And since we're assuming that the amount of charge transferred from the sweater is equal to the amount of charge gained by the balloon, we can say both Q1 and Q2 are equal to the same number. So therefore we can say this kq squared by r squared equals to this. And once we solve for Q after plugging in the values, we get the value of Q to be around 116 nanocoulombs. Now if we check for the reasonableness of this answer, we can say that for this many number of coulombs to be transferred, there has to be this many number of charges that has to be transferred to and from the sweater. And this number, which is pretty high, is very reasonable because we know although the charge transferred is very low, there are a lot of electrons that are going to be transferred from the sweater to the balloon. So this number, this high number, which is the number of electrons transferred, tells us that our answer, which is 116 nanocoulomb, is very reasonable.